Okay, here we are. So first things first, I just want to remind everyone that we're off on Monday, if you can believe it. They did at some point decide that we should have a handful of days off instead of spring break. And guess what? Monday is one of those days. So yeah, let me see. Yeah, yes, yay. Well, I mean, we were supposed to have a whole week off. But you know what happened. So let me just show this to everybody. There it is. Okay, just a quick reminder. So there's a list right here somewhere. Yes, exactly. Yeah. I mean, those other days I wasn't teaching anyway, or at least not at Purchase. So this is the first actual day off that many of you will have had. So yeah, there it is. There's the official list. So we had a Tuesday, we had a Wednesday, and now finally we have a Monday. Woohoo! Okay, so that would be this coming Monday. So in other words, I'm going to try very hard. I mean, it's become such a force of habit for me to send out the invitations. If I accidentally send you an invitation for Monday, then just ignore it. Okay, it's not unthinkable that I could just sit there and say, "Oh my God, I forgot the invitations," and then there they go, and then I just realize, "Oh no, there's no school on Monday." So if that happens, you can just ignore it. There is no school on Monday. Now, with that being the case, then we are winding down the semester, obviously, as you know, and chapter 12 is the end of the semester. Once it's done, there's nothing left for us to do except review for the actual final exam. So today, what we're going to do is three things. I've got one video that I'd like you to see about correlation and how to interpret it, basically, is what it's really all about, more than the calculations. Then we'll finish up the chapter. And then there is a chapter 12 problem set, which I'd like to do today. And let's see. Oh, I didn't open it, I guess. Hold on one second. Oh, this weekend for sure. Yes, I've been pushing everything. Oh, it's just been insane here. This is the busiest time of the year for me by a long shot. So yes, I'll be making every effort to get them done during the weekend. So sorry about the delay, but I've just had I have so many exams to correct. It's just unbelievable while still getting everything ready for the exam. So this weekend for sure. But anyway, oh yeah, so anyway, so we need the chapter 12 problem set. Let me just open it up so you can see what it looks like. It's not that long. It's actually, where is it? There it is. But yeah, so I'd like to do that today because that way, the next time we meet, which is a week from today, we can spend the entire class on the sample final. All right. So I think we can get all that done today. So again, the video, rest of chapter 12 and the sample final. And then next Thursday, we can go over the sample final. I think I've posted the sample final already if you want to look at it. Let me just double check that. You may have noticed that they've slightly redesigned their website here. All of a sudden, all this stuff is hidden under quick links. Yeah, I don't remember them telling us about that, but okay, what are you going to do? Where are we? Okay, let's just check this out. I just want to make sure that I posted the sample. If not, I'll take care of it. Yes, there it is, as a matter of fact. Okay, now remember, it's only 11 and 12. There's nothing else on there. It is not comprehensive. All right, so there's your sample final. And so you'll have a week to work on it because obviously we're off on Monday. But it's not, again, it's really not all that long. I think that the first test was definitely the longest. This one, I mean, it's just, the thing is that questions are fairly time consuming. There's not so many of them, but no, it's a pretty good representation of what we've been doing. So we'll save that for next week. All right, so in the meantime, let's take a look at this video. Now, what they're going to be talking about is this idea that correlation, which we started to talk about, let me just, in fact, I'll tell you what, before we do the video, let me just get back into the notes for a few minutes, just to remind you what we've been going over, just in case you start to forget what we were doing. So the measures of association represent the degree to which two variables tend to move in the same direction. And so there's two measures that we'll be looking at, covariance and correlation. Now, as it turns out, before we got started looking at these measures, we were looking at graphical representations of the relationship between two variables. So, for example, if we wanted to analyze the relationship between, studying time and GPAs, we would certainly expect that more studying time leads to higher GPAs. And so we can illustrate that with what we call a scatter plot, where the data is over here in the upper right-hand corner. In this case, there's no negative numbers, so all the data are in the first quadrant. And you can see each of one of these points represents a single member of our sample, which is a single student's studying time and GPA. And what we're really looking for is this pattern right here. And so you can see the pattern shows that there's a tendency for the points to move in towards the upper right-hand corner, which means that when X is increasing, Y is also increasing. Not always by the same amount though. If you notice that the points are scattered around this trend line, the relationship between X and Y is therefore, it's very strong, but it's not perfect. In other words, your GPA is not 100% determined by studying time. There could be other factors as well. Like your interest in the topic, for example. I mean, you know perfectly well that, you're going to do better in classes that you like than in classes that you don't like. So same amount of studying time in a class that you like and don't like might provide very different results. So that's why the points are not all perfectly lined up on the trend line, because other variables besides studying time are influencing our GPAs. But in general, you notice that it is a very strong connection. Any way you look at it, more studying time is bound to lead to higher GPAs. So there's a positive relationship between these two variables. In the case of the texting, we looked at that example as well. And so here we expect that the more time somebody spends texting, the less time they're studying, therefore their GPA will be lower. And so we can represent that with this scatter plot. And so you can see the pattern of the dots is moving in the opposite direction towards the bottom right-hand corner here, which indicates that as X is increasing, Y is decreasing, and vice versa. So the more texting is lower GPA and vice versa. So the trend line shows again that while the points tend to move in this direction, other factors could be getting in the way too. Other things could be causing your GPA to fall besides texting time. So again, the relationship is not perfect, but there is what we would call a negative relationship here, in the sense that as X goes up, Y tends to go down and vice versa. And then we had the third case of GPAs and heights, where there's no reason to believe that the two variables are related to each other at all. And so the points are basically just randomly scattered around the line. And the trend line itself is flat, which means it has a slope of 0. And that it's a sign that the two variables are not related to each other, or in other words, they're independent. Now, what we would like to do, and what we're going to do, is not just rely on these scatter plots to understand the relationship between X and Y. What we're going to do is create numerical measures that help us quantify this relationship. In other words, it's obvious that this is a strong relationship. The question is, how strong is it? Is it stronger than other relationships out there? We don't know. We need numbers to make decisions like that. So we're going to measure this relationship with two different alternative measures. The first one is called the covariance, and the second one is called the correlation. They both have their advantages, but it turns out most of the time the correlation is actually the better of the two measures for several reasons, which we'll get to as we go through the chapter. So what the video is going to do is basically discuss this whole concept of, I think they're just going to talk about correlation, but what they say about correlation applies to covariance as well. But what they're trying to get at is this idea that it's easy to misunderstand what correlation actually means. Okay, so here's the problem. What happens if, for example, you have two variables that tend to move together? It doesn't necessarily mean that one is directly responsible for the other one. Like, let me show you an example of this. This is like a little side note here. We do not want to misinterpret these measures of association if there is a strong connection between two variables. It doesn't necessarily mean that one actually causes the other. All right, so what do I mean by that? All right, let's look at this one. There actually was a very classic case in economics where this happened. The economist William Stanley Jevons the 19th century, let's say, noticed in his research that there was a tendency for sunspot. Now, does everyone know what a sunspot is? A sunspot, that basically refers to, the sun is continuously giving off magnetic radiation. Yes. And so, but what happens is sunspots grow and they shrink over time as the sun, the sun is very active, let's say. And so it has all these sunspots on its surface. But the thing is, they're not permanent. It's not like craters on the moon, which are permanent. Sunspots rise and they fall. They tend to go up and down. Sometimes there's a lot of sunspots. Sometimes there's not so many sunspots. And in fact, when technology was not nearly as advanced as it is now, they used to cause havoc with radio reception. When there's a lot of sunspot activity, it was harder to hear the radio. And so what it represents actually is fluctuations in the magnetic field on the sun. So they go through cycles. Some years there's a lot of sunspots and some years there's not. So William Stanley Jevons looked at a lot of data and he said he noticed there's a tendency for sunspot activity to fluctuate at the same time as the economy or as the business cycle in the UK. Now, I don't remember if he said that sunspots tend to go up when the economy's strong or vice versa. Actually, we can probably find a discussion about this on the internet. So he came to the conclusion that sunspot activity was actually causing the business cycle. In other words, that's the bottom line. So in other words, he concluded that sunspots were actually causing the business cycle, which, as you know, represents fluctuations in the economy. So of course, it turned out to be a logical fallacy. It turns out that, to a large degree, it was just a coincidence. So this is the kind of thing we have to watch out for. It's easy to make logical mistakes when we look at data and note that there's a positive correlation or covariance. So another good example, I saw an article on the internet once where they're showing you all these variables that tend to move together and where it might be easy to conclude that there's a causal relationship there when there really wasn't. For example, researchers determined that during the 1980s, there was a strong increase in both professors' salaries and liquor sales. Okay, so in other words, it would be tempting to conclude that the higher professor salaries were responsible for the higher liquor sales, but in fact, they were both caused by a third factor, the state of the economy. So in other words, what was happening in the 80s was the economy was unusually strong. And so naturally enough, when the economy is strong, there's a tendency for salaries to rise and for sales of all products to rise. So in other words, the fact that they are connected, in other words, the fact that they happen at the same time doesn't guarantee that one is responsible for the other. And so it's an easy logical fallacy to make, to see two variables that tend to rise or fall together and conclude that one is responsible for the other, because it isn't necessarily the case. Now, with our examples up here, though, I would say that here we're probably on more solid ground, assuming that one of these is actually causing the other. Like, I think it makes sense to everyone that studying time would tend to cause higher GPAs, or that texting time would tend to lower them. But there could be other factors that are connected to GPAs, but just happen to be a coincidence. Like, what if it turns out that GPAs are higher during years where the weather is nicer or not nicer, or something like that? So, for example, what if I told you that, and we don't know, I don't know if this is true or not, but let's just say, suppose that it turns out that GPAs tend to be lower during years when the weather is unusually nice. Does this mean that the weather causes GPAs to fall? No, what's probably happening? No, most likely the warmer weather discourages students from studying, which is the reason why GPAs fall. So anyway, now this is completely independent of the calculations. The chapter really is all about calculating these two measures, covariance and correlation. But I wanted to give you an idea of where the video is heading, because they're going to talk about this at great length, how to avoid this logical fallacy that a positive correlation or covariance implies that one variable causes the other. And so Jevons, actually, unfortunately for Jevons, it made his reputation suffered quite a bit, because this is what people know him for, even though he was a good economist. The fact that he concluded that the sunspots were directly causing this business cycle meant that people were not going to take him as seriously as they might have, because it turned out that it wasn't really happening. In other words, there was no direct link between sunspots and the business cycle. It just, during the 19th century, just by coincidence, they tended to rise and fall at the same time. And then, of course, in the 20th century, that turned out not to be the case. So it showed that this relationship was just a coincidence, and that he incorrectly assumed that the sunspots were actually causing the business cycle. So poor Stanley, William Stanley Jevons, yes, he's very well known, but sadly enough, not maybe for the right reasons. Okay. Well, anyway, what I'm going to do now is, now that you should be ready to watch this video, and it should hopefully make sense. And when we're done with it, we're going to go back and look at the actual formulas for calculating covariance and correlation. Okay. They're a little bit messy. There's several steps involved, but they're not that much different. Once you've gotten through with the variance, if you can do the variance, you can do the covariance and the correlation. They're not radically different. They may look scary when you see them written down on the page, but it really isn't that big of a deal. Okay, so all right, so let's get this video going. All right, let's check this out. Hopefully, you'll now know everything you ever wanted to know about correlation and causality. Mm.
If we look at ASC sales data over the past 10 years, and even more proof, if we look at Nicholas
All right. So I thought they did a pretty good job of explaining what this field is all about. They never actually mentioned covariance, but it doesn't really matter because covariance and correlation basically measure the same thing, but in different units. So I thought that, yeah, they laid it out very nicely there. So you have a better feel for what correlation really means, what it's all about, and what it's attempting to measure, and how we have to be very careful in the way we interpret it. Because it's easy to come to reach logical fallacies by looking just at correlation data. Okay, in other words, the whole point is you should never assume without further knowledge that correlation is the same thing as causation. Now, if two variables are correlated, they may very well be causing each other, but it doesn't guarantee anything. That's the whole point of this. All right, so what we still need to do here is actually do the calculations. So in other words, what are these measures, or how are these measures actually calculated? And why is correlation typically seen as a better choice than covariance? All right, so we'll start by looking at covariance. Now, with covariance, just like with correlation, the covariance between two variables can be positive, negative, or zero. And there's three things that can be happening. Either they're both rising together, they tend to go up and down at the same time, which means there is a positive covariance. They tend to go in opposite directions, which means there's a negative covariance, and they tend not to be related to each other at all, which means the covariance is zero or very, very close to it for two things that have nothing to do with each other. Like in our example about GPAs and heights, the covariance would have been zero. For our example about GPAs and studying time, the covariance would have been positive. And our example about GPAs and texting, that would have been this case where the two are negatively related. All right, so here we're going to look at a case where we have a corporation that's analyzing the relationship between their sales and their profits. Okay, now clearly, the hardest thing for a corporation to do is increase its sales. Sales are everything to any kind of business enterprise. If you don't have sales, you do not have profits. It's just that simple. If people don't buy your product, you're not going to make any money. So obviously, all these different corporations do their best to figure out what products to sell that people actually want to buy. And a lot of products have disappeared from the market over the years because people didn't really want them. But if sales are going up, almost without fail, profits are going up as well. Not always. You might have a year where sales went up, but your costs went up even faster, and then you might find yourself actually suffering losses. But let's just say that in this example, X represents sales and Y represents its profits. And if you notice, we chose X and Y on purpose because you'll agree, I think, that between the two variables, let's say, let me make a note here. X equals sales, Y equals profits, because profits depend on sales. Sales do not depend on profits. So therefore, X becomes the independent variable, as it's called, independent, and Y is the dependent variable. Okay, so with that being said, let's say that, now here's a second example where instead of analyzing the relationship between sales and profits, we're going to take a look at the relationship between costs of production and profits. Now, every business enterprise produces products for sale to the marketplace. It is not free to produce products. In other words, if you go to a Starbucks and buy a cup of coffee, they had to pay for the beans, the cups, the lids, the sugar, the milk. They also had to pay people to make the coffee, And they had to buy a lot of equipment to make all of this possible. So the costs of production are a primary driving force behind profits. The higher your cost of production, the less profitable you will be. It's just that simple. So in a case like this, if we allow Y to represent profits but X to represent costs, well, you would imagine that the covariance between these two variables would be negative, because when the costs of production go up, holding everything else constant, you would expect our profits to decline. And that's exactly what happens. But we want to show it or demonstrate it with our covariance measure. Another possibility here is that we can analyze the relationship between temperatures and profits. So unless the corporation produces seasonal products like, I don't know, surfboards or something like that, there's no reason to think that there's a connection between temperatures and profits. So in a case like this, when we calculate the covariance measure, you would expect it to be very close to zero. Now, here we go. Just like with the variance and the standard deviation, there is a separate formula for sample covariance and population covariance. Also, I'd like to point out that here we're looking at two different samples or populations. So we'll adopt the following notation, and we'll see it on the next slide when we look at the formula, where there are two samples. Let's call them X and Y. So this Xi is an element of sample X. And this Yi is an element of sample Y. And equivalently, this is X bar is the mean of sample X, and Y bar is the mean of sample Y. So you can see that's why the notation looks different. We never had Y before. We didn't need it. We only had one sample. It was called X. Now we have Y as well, and we have to be able to tell them apart. Now the N represents the common sample size. And what do I mean by that? Both samples must have the same number of elements. They both have N elements. Otherwise, this doesn't work. And then finally, if you notice S, now you might recognize that S, we've used it before for the sample standard deviation. So how do we know that this represents covariance? Well, because of the two subscripts. Okay, so in other words, SXY is not the sample standard deviation any longer here. It is the sample covariance between X and Y. So for whatever reason, statisticians did not create a separate symbol for covariance. So they'll use this one, S, but to remind you that this is actually the covariance, we have these two subscripts, X and Y. So that way you don't get confused, okay? Now, let's take a look at an example. And by the way, when you look at this, it doesn't, I mean, we haven't done an example exactly like this before, but what you're doing in the numerator is you go through the list of X's and Y's from the two samples, and for each X, you subtract the mean, and then you do the same thing for Y, and then you multiply them together. Finally, at the end, you add them up, and you know that because we have the summation operator. All right, once we've done an example, you'll say, oh, that's not that hard. It might be time consuming, but that's different from being hard, isn't it? Yes. All right, so let's look at the data we have. We have 2 samples with 5 elements. And so here they are. And so you've got 5 elements in X, 5 elements in Y, and we're going to calculate the sample covariance between them. So what should we do first? Well, the first step is always going to be to calculate the sample mean for X and the sample mean for Y, because we'll need them in the formula. Okay. I'll give you a minute to catch up, and then we're going to go ahead and calculate the 2 sample means, X bar and Y bar. And of course, nothing's changed. We're still going to just add them up, add up the elements, and in this case, divide by 5, the sample size. All right, so the first one, X bar, luckily, I mean, these numbers are very simple, and there's only 5 elements, so you may be able to do this in your head. The sample mean for X is 1, as it turns out, because if you add up all those elements, you get 5, of course, and there's 5 elements in the sample, and that ratio is equal to 1. And then we do the same thing for Y. And what we're going to wind up with is, in this case, I'll show you when we're ready. 3. Okay, so in other words, if you add up all the elements in sample Y, you'll see that they add up to 15. The sample size is 5, and so therefore we have 3. Now, for the next slide, what I'm going to do is go back and grab the sample data just so you can see it on the same slide. Let's see if I can fit everything on there. Just so you can follow along and see exactly what we did. This is, of course, the tricky part, plugging in all the numbers into that formula. All right, so here, okay, let's see. I'm going to do this. I'm going to find room for these guys so you can see everything all in one place. Oh, that's not going to work. All right, let me do this by hand. Hold on 1 second. Okay, and also we need to remind ourselves that X bar equals 1, Y bar equals 3. That should do it. Okay, so now let's analyze what's going on down here. So also, maybe I should grab the formula again so you can really see everything all together. Oh, okay, good. It does kind of fit. There we go. I think that'll do it. You should be able to see it. All right. So in other words, here's what we're doing. This is x1. This is x bar. This is y1. This is y bar. This is x2. And again, this is x bar. We multiply that by, and this is y2. Oh, there's less room. No, wait a minute. No, hold on. I bet I can fix this. Okay, so this is x3. This is y3 minus y bar. This is y4, sorry, x4. It's always x and then y. And then down here we have x5 minus x bar, y5 minus y bar. And oh, by the way, if you didn't notice, in the denominator, you're divided by n minus 1, so that's 4 rather than 5. Now, this all turns out to be -1. Okay, that should do it. So the covariance of these two samples is -1. Now, negative means that they have a tendency to move in opposite directions. Now, it's hard to say when you've only got 5 observations. If we were to try to draw a scatter plot, it would not be terribly meaningful because there's so little data, but there's a tendency for the two variables to move in the opposite direction. Now, the problem, though, is that the covariance doesn't tell us, or at least it's not very helpful in determining how strong is this relationship. In other words, the fact that they're negative could mean a lot of things. For example, it might be that if we did draw a scatter plot, you could have these two different scenarios, which I think you'll agree are very different from each other. So maybe you could have like this. So sure, there's a negative relationship there, but it's not very strong. These points are not really that close to the line. Whereas over here, you might get something like this. So this one has a relatively weak negative relationship. And this has a strong negative relationship. Now, this is one of the reasons why the covariance is not as useful as the correlation measure, because the number itself, it's hard to tell what that number means. There's one, is that a strong connection? Is that a weak connection? The rub here, and I'll just mention this too, is that the covariance is influenced by the units in which the data are measured. So -1, it tells us that the relationship is negative, but it doesn't tell us how strong this relationship is. So this is sort of a hint as to why we would probably prefer to use the correlation coefficient. But before we go into our discussion about the correlation coefficient, what I'm going to do is show you the corresponding formula for the population covariance. And so I'm going to copy this one again so you can see them side by side. And let's see what the differences are. So this is our sample. Let's move this over here. This is the population version. So if you notice, we of course have Greek letters. This is the lowercase sigma. Now, if you notice here, instead of x bar, I've got mu x bar. This is the mean of population X. You notice the little subscript here. We haven't had that before because we only had one population. We didn't need to tell them apart. Now we do. And so the way we do that is with subscripts. And then, of course, remember the N, capital N is the population size versus lowercase n. But again, remember with the variance and standard deviation, the denominators were different. The same thing is true here. The denominators are slightly different. The population version is divided by n, and the sample version is divided by n minus 1. And this is exactly what we saw when we compared the population variances to this, the population and sample variance, as well as the population standard deviation and the sample standard deviation. Okay, so we're not going to do a separate example for this one. Instead, we're going to dive right into our discussion about the correlation. We want to see how it's different. And we also want to understand why it's a better measure of association. Okay, so, and I think they mentioned this in the video too. Why is correlation a superior measure? Oh, by the way, remember in the video they were talking about Carl Pearson, who did all that research about heights and of sons and fathers and all that. It doesn't show here, but the proper name, this correlation coefficient that we're using here, is actually called in statistics Pearson correlation, named after Carl Pearson. So he was like a real pioneer in statistics. And a lot of what we have came directly from him. So they mentioned his name in the video. He's one of the real superstars in the history of statistics. And so this measure, among many others, was his idea. So anyway, so correlation is closely related to covariance, but here's one tremendous advantage it has. Because of the way it's defined, the value can only take on a value between -1 and +1. And that means that we can tell right away how strong the relationship is between our variables, not just the direction, but the strength. All right, so I'm going to illustrate that for you now with a couple of plots. Okay. So let's look at a few typical cases. So we'll do, I guess, 2 positives and 2 negatives. So for example, let's say we have a positive correlation, but in the first case, it's very strong. In the second case, it's very weak. Okay. So let's assume that the points can go in any of the quadrants. For certain types of data, that is the case. So you can see what's going on here. Look how strong that connection is. The points are all really close to that line. And so let's say here, I'm just going to make this number up. Let's say the correlation is 0.9. Now, because it's correlation, that 0.9 means it's very close to the maximum value of 1. So when I see a 0.9 correlation, I know that I'm looking at something like this. Whereas, like I said, with the covariance, it's very difficult to be sure what that number is telling me. On the other hand, what if I have something like this? Well, you get the idea. The points are pretty far scattered around this line. So here, let's just say the correlation is 0.3, and I'm just making these numbers up, but you get the idea. 0.3 means the connection is positive, but it's not particularly strong. Whereas in the left-hand side, that's a strong relationship. And you can tell right away simply by looking at the correlation itself, because it's going to be somewhere between positive and -1. Now we can do the exact same thing with negative relationships. There'll be strong ones, strong negative relationships, and there will be weak negative relationships. Oh man, so let's see. I'm sure you can visualize where this is going. So this first one on the left will be a strong negative relationship. And over here, we have a weak negative relationship. So this one might look something like this. So it's a negative relationship, but look how close those points are. Let's say that this is a correlation of -0.8, let's say. It's very close to the minimum of -1. And over here, oops, we have something like this going on, where the points are really not that close to the line at all. So here we'll say that this is a correlation of -0.2. It's a really weak connection. It's negative, but it's very, very weak. And then, of course, another possibility is that there's essentially no relationship between the points at all. Like our example with the temperatures and it was the heights and GPAs, where you would expect no connection whatsoever between how tall you are and how high your GPA is. So you have something like this. We would have here, we'd simply say no relationship. Or you can think of that as independent variables. And there's just literally no pattern here. It goes up, it goes down, it goes all over the place. So the trend line is essentially flat. So here you would say the correlation is 0. Because the two variables have nothing to do with each other. But you can see the number now is very meaningful. Okay, that's extremely important. So I can tell just by looking at that number, not only the direction of that relationship, whether it's positive or negative, but I can also tell how strong it is. Now, I'm going to start by introducing you, like with the covariance, there is an equivalent version of the correlation measure for both samples and populations. And it turns out that they're derived from the covariance measure. Just like the standard deviation is taken from the variance, the correlation coefficient, as it's called, is derived from the covariance. In fact, it's basically an adjustment to the covariance measure. So when you see these variables, they should look very familiar. So we'll start with the sample correlation. So we're going to use the letter R. This will be our sample correlation coefficient, as it's called. This, as you recall, is our sample covariance. And see, what we did here was we simply divided, this is the standard deviation for sample X. And this is the standard deviation of sample Y. And so, like I said, it's just essentially an extension of the covariance measure. And by dividing out those two standard deviations, we're guaranteeing that R is bounded between negative and positive 1. I'll put that reminder up here. And that's because of the way we defined it. So what we're going to do now is take our results from that last section where the sample covariance was -1, and we're going to now calculate the equivalent correlation coefficient. Now, so what we're going to do here is we take as our starting point SXY is -1, which you recall from before. But now, unfortunately, we have to go through all the trouble of calculating two new standard deviations. So I'll just quickly show you what they look like. I know that you already know how to calculate a standard deviation. So the standard deviation of X turned out to be 2.1213. And of course, you recall that, the sample standard deviation formula looks like this. And that's what we're doing down here. But there's a subscript here to remind you that this is the standard deviation of sample X and what we've done here is, of course, remember X bar is 1. So this is X1, this is X bar, X2, X bar, X3, X bar, X4, X bar. And so you remember doing this from before. So then we take the square root once we've added them up and divide it by 4, and we get approximately 2.1213. Now we have to do the same thing for sample Y. Except that this time the letters are different. That's the only difference. So we already know that Y bar is 3. All right, and so let me just write up here. I'll put this little X here just as a quick reminder, because on the next slide, we're going to introduce SY. It's the same thing except with Y's instead of X's. Okay. So then SY would be written as Okay, so again, you're right. I mean, you can see that the x's have been replaced with y's. And so coming down here, this is y1, this is y bar, y2, y bar, y3, and y bar, y4, and y bar. And finally, here we have y5 and y bar. And you can see for yourselves at the end, that turned out to be 2.2361 approximately. So you can see calculating the correlation is going to be a fairly time-consuming process, but as long as it makes logical sense, that's fine. All right, so then what do we do next? Why did we go through all these steps? Well, we're going to plug these into the correlation formula. We have all three pieces that we need. And what are those three pieces? Again, it's this covariance and the two standard deviations. So let's plug them all in. And what we're going to find out is how strong is this connection. And remember, we did say that the covariance is -1, which means there's a negative relationship, but we still don't know how strong it is. That's why we want the sample correlation coefficient. All right, let's do it. So you plug in all the numbers and, oh, there you go. It's -0.2108. So this is a fairly weak negative relationship, as we saw in the graphs earlier. So we think of this as a weak negative relationship. -0.2. Remember, given that the maximum negative number is -1, this is getting pretty close to 0. So the connection is not that strong. It is negative. Now, remember before we did say that with a covariance, we couldn't really be sure how strong this relationship was, but now we do. We know, we can see for ourselves, it's very weak. So the two variables are not terribly strongly related to each other. We don't know what they are, but they're not all that strongly connected. All right, now the last thing that we need to do is introduce the formula for the population correlation coefficient. Of course, if there's a sample version, there must be a population version, which will of course include Greek letters. Greek letters, yes. So there's one though that you haven't seen before, I bet. So let's take a look at this. And what's interesting is that this time, the actual calculations are identical for the sample and the population correlation coefficient. The only difference is the Greek letters versus Roman letters. So in fact, I'll do the same thing. I'll copy this onto that slide so you can look at them side by side. And so let's look at them together. And you can see, there's a brand new Greek letter here. This is the Greek letter rho, as it's called. And whenever you see rho anywhere, it means the correlation. Correlation. Certain Greek letters are always used for the same thing, like delta always means a change. Theta always means an angle. This is one of those cases, rho always means correlation. So up here we have the population covariance. And down here you have the standard deviation. Of population X. And over here, we have the standard deviation of population Y. So over here, this is the sample correlation. And you can see they're identical to each other except for the letters that we chose to use. The formula is exactly the same. All right, so chapter 12 is now officially done. We've seen the video, so even though we don't have that much time left, what I'd like to do is at least take a look at the chapter 12 problem set. So here's the plan. We'll do on next Thursday, remember, no class on Monday. On Thursday, we'll go over the rest of the chapter 12 problem set. And we will also, of course, have to do the sample final, which is entirely based on chapters 11 and 12. Now, if we finish, which I think we will, then I will post the final exam, and that means that we're completely done with everything. Now, normally, if we were in person like usual, then we'd have to come back the following week and take the test in the classroom. But we don't have to do that here. So if we're done next Thursday, which should be, I think, the 6th of May. Let's confirm this real fast. May the 6th should be next Thursday. Yes. Now that means that if I post the exam on the Thursday, we don't need to have any more classes. Okay, then we're done. We could potentially have had a class on Monday the 10th, but I don't believe that that would be necessary. Okay, the 10th was meant to be the last day of the semester. But if we're completely done on the 6th, I say that we take the day off so you can have more time to work on your final. Now, the final is no longer than the other exams you've already had. Okay, in fact, if anything, it's probably a little shorter, certainly than the first midterm. The only thing that remains to be determined is when they need to be ready. Now, the official final exam week starts on the 13th. So that means in principle, you can probably have until, God, more than a week, probably as far ahead as maybe the next Monday. I'll let you know about that though. But I'm telling you, this is not going to take that long. And also maybe you'd like to get it out of the way before you start your other classes' final exams. So that we'll figure out next Thursday when we get together. But my suspicion is that we'll be completely done on the 6th, and then will not have to have another class on the 10th. All right, does that sound like a good plan? Okay, I'm going to take that as a yes. Okay, I know it's sad. I mean, nobody wants the semester to end. It's been so much fun, but you know what? There's more math classes available at the school if you're really, excited. So yeah, let's do it that way, because like I said, all that remains to do, it would be next Thursday. And then you could have more than a week to finish it, maybe even a week and a half. Well, thank you. I think it was a good semester. I think we learned a lot of interesting stuff. And now, in fact, I think more than that, it actually stimulates your understanding of math, and that way, when you encounter it again, it'll be easier to learn new math concepts or else apply them to whatever it is that you're doing. And also, it's just interesting for its own sake. And of course, thanks to the videos, we also got to see a lot of real world applications of a lot of this material, which is really awfully important too. It's not enough to learn the material. It's really important to understand why we're doing this. It's like, well, why do we need to know all of these concepts? Now, here's a perfect example of what I'm talking about. One day down the road, when you're earning a lot of money and you have money to invest, you might start to wonder, should I buy stocks, for example? Well, how do you understand how risky a portfolio of stocks is? These measures that we've learned in this chapter will be exactly what you need to understand what kind of returns you're getting from your stocks and how risky they are. So this kind of information is extremely useful in a lot of areas. In fact, statistics was deliberately designed to be useful for practical real-world applications, more so than a lot of the other topics that we've looked at. But anyway, so let's at least get this thing open while we got a few minutes left. The chapter 12 problem set, I don't want to rush through it, but I want you to see where we're going. So in part 1, we have a sample. Now, if you notice, I've highlighted the word sample because I want to make sure you recognize that at least one of two of these right down here, for the variance and standard deviation, the formula is slightly different for a sample and a population. So therefore, if you don't notice this word here, you might get the wrong answers, at least for these two. That would be no good. All right, so make sure you notice when you start any kind of problem in this chapter, whether you're dealing with a sample or a population. And here we have a population. It says it right there. Make sure you pay attention because otherwise these two will be wrong. Okay, so how would you start this? Now, the mean is easy. In fact, the measures of central tendency are quite straightforward. I think you'll agree. So why don't we at least get started on this? And then, like I said, we can finish it up next Thursday. What's today? The 20th. When I see you again, it'll be May. Oh my God, is that possible? I don't know where the time went. It seems like just 2 weeks ago, it was still cold and rainy and miserable. And, you know, all of a sudden here it is, and it's almost May. So let's start with a couple of these. Now, with the mean, what you're doing is, of course, taking X bar add them up, divide by, here there's 6 elements, and that's going to give me 9/6, which is 1.5. And you're done. It's so simple. Okay. Not a problem. Okay, everybody gets the mean. Now the median, remember, there's that one extra step we have to go through. We have to sort the results. We have, or sorted sample, let's call it. We have -1, 0, 1, 2, 3, 4. Now, because we have an even number of observations, we will average out the 2 middle observations. Okay, so that would be the 1 and the 2. $1.5. Okay, just like the mean. And remember, we did see that sometimes this happens. Sometimes the mean and the median and the mode are all the same. Now here, though, the mode, if you look at the sorted sample, you'll see that, oh boy, there do not seem to be any repeated values. And that means that the data will not exactly be symmetrical, but it could be very close to it, since the mean and the median are the same. All right, so you can see these are pretty straightforward. The range also requires us to use the sorted sample. So here we have the range equals the largest element minus the smallest element, which equals 4 minus a minus 1, which is equal to 5. All right, so those are the easy ones. Now for the variance, keep in mind this is the sample variance. So for this, what we're going to do is we do not need to sort the data for this. Now this one's going to be a little tricky because the mean is 1.5, so we have to be very careful with our calculations. So the variance is S squared So what we have to do is go through the list of elements, and then in each case subtract the mean, which is 1.5, square the results, and then divide by n minus 1. All right, well, let's try that. So first you just plug in the numbers. Now go through the list up here. If you use the sorted set, that's okay, but they do not need to be sorted. It will have no effect on the results. And I'm going to run out of room, so I'm going to continue on the next line. Oh, in fact, I'm at the bottom of the page. Isn't that nice? All right. And of course, there's 6 elements, so the denominator is 6 minus 1. Oh, sorry, let me just scroll down. Here we go. This is where we were. So now what you've got to do is, I would recommend you simplify this by calculating the differences within the parentheses before you square them. All right, so if you do that, let's see what you would get. Okay, so for example, you'd have negative 2.5 squared plus negative 1.5 squared plus 2.5 squared, 1.5 squared, negative 0.5 squared, I'm running out of space there, negative 0.5 squared, and then finally the last one would be positive 0.5 squared, all divided by 5. Now, when you go through and calculate these individually, this is 6.25, 2.25, 6.25 again, 2.25. All right, so if you add up those numbers in the numerator with your calculator, you should get 17.5 over 5 equals 3.5. That's your sample variance. Wow, after all that work. Now, how about the standard deviation? Well, if you recall, the standard deviation is nothing but the square root of the variance. So when we get to that, oh, here it is. We can just write that S is the square root of the sample variance. And that's about 1.8708. So you basically are getting 2 measures for the price of 1. I mean, realistically, all that work is actually getting you 2 measures. Okay, so those are done. Now, of course, there's a second question here that we'll have to save for next Thursday. And that plus the sample final will be what we're going to do on Thursday. Of course, if you've got any last minute questions or if you're not sure about something, we can go over it then. And then when we're done, I'll just post the final. And then if you're stuck, if you have problems, you can send me emails while you're working on your final. But I'm pretty sure that we won't need to have any more than one more class, just next Thursday. Wrap this up, and I believe that will take care of it. So, well, we finished a little early. That's okay. It's better than running out of time. That's always the biggest challenge with covering this much content, making sure you don't run out of time. That to me is much worse than finishing early. Okay. So we made it under these very unusual circumstances. We made it. Hopefully this will never happen again. So, all right. In the meantime, if there's no last minute questions, I will see you all not on Monday, but next Thursday. All right.
Thank you.
Thank you.
Okay. You're welcome. See you later. Bye.